Might as well. Hey, everyone. So what you see here is different from what you've seen before. Jen and I were just chatting, and we don't have anyone viewing yet, but we'll get people rolling in. So Jen and I were just chatting, and I was showing her topology optimization. This is what this is, and yeah. So that's kind of that's the goal. Is we want to use Omniverse to produce engineering load cases to be able to run an optimization like this. And let's see, Jen, what were you were just asking? This kind of gray transparent box around the outside.
Yeah, because it's like I assume that was the one you started with, right?
Yeah,
And then you just went, you put in your parameters, right, saying I want it to do this, this, and this, and then you hit go, and then it just went boom. Here's a model.
pretty much. Let's see here, materials, models. It's showing me the results. I haven't used this software a ton, but yeah. You just draw this chunky thing, and you can do that for all of your parts in an assembly, so that as your mechanism is moving, nothing interferes with anything else, right? And then so you just draw this chunky thing, and then you have to figure out the loads. Well, you you should. This software actually has a really cool feature. It will use AI to guess at some loads if you give it like a use case, like automotive or aerospace. It's pretty cool. Like if I go to the load cases, yeah, I just said automotive. Give me some automotive loads. Make a guess, and it did, and it didn't. It did a pretty good job coming up with like use. I think it uses AI even to come up with some load cases.
And can you download these models?
Yeah, I can download an STL, and in fact, if I open up, um, let's go to Exchange. Refresh. Come on. I wasn't on the VPN when I first opened this, and so now it's. Am I on the VPN
You
now?
might have to reopen Omniverse.
Oh dear. Usually you can just refresh it. Well, let's relaunch Omniverse. All right. Just to give us a minute here. Launch it. Yeah, I'm good. I'll open the RC car scene that I've worked on before. And in that scene, I've got this in there already. And after this, we can go back to some of that. Although instead of that remote control car, and I'm really curious what you all think. Shout out if you're in the lobby and you've got an opinion. We can work on a remote control car that once we're done, I can release all of the CAD files, and it's a small enough thing that you could build your own copy of this remote control car. We could even come up with the bill of materials, like so you can go buy the nuts and bolts off of a McMaster, and you can 3D print most of the parts and kind of that sort of thing. So we can do our own design of a remote control car, so smaller scale, but you can make it yourself, or we can rig up the Sierra cars RX3 or EV3, maybe the EV3, their electric version, and we can rig that up and get it so we can drive it around with an Xbox controller. I mean, either one we'd be able to drive around, but so I'm curious what your opinion is if we should do the bigger Sierra Cars car, or if we should do a remote control car design. So let me know your thoughts. And let's see here, but let's open up this scene. Here we go. Let's go to Exchange. Now we're talking. Actually, we want to go to right here. This is the kind of thing we can do. But yeah, here's your remote control car, and you can see that same part we were showing. Here it is in ABS, in Omniverse, right here. Or maybe that's a little different version, but yeah, that's the same. Let's see.
So, did you make all of these parts in that program?
Just there we go. Sorry, I was getting an echo because I had the YouTube stream live in a different tab. Okay, most of these parts So some of these parts I made in NX.
Okay.
So let me show you. Great questions.
What is NX? I'm not familiar with that.
NX is a CAD software. It's
okay.
so if you worked at an aerospace company such as Pratt and Whitney, or if you worked at, I think Daimler Chrysler uses NX for their designs. It's maybe a similar in scale to CATIA V5, which is like Boeing and BMW use CATIA V5.
Interesting. Just learned something new. Hey, Zia. I see Zia's hanging out.
Let me just open. Let me see if I can open it up real quick. There we go. Oh, great. Here it is. So here it is in CAD. Here I even have a LiDAR scan. This is the differential I'm planning to use. And I just have the parts roughed out for now, just for dimensions. And you can see I've got all these sketches and stuff. I've been able to use those. I'm actually designing the car from, you decide like, well, what camber do I want the wheels to have? What roll center? What are the dynamic properties that I want? And so then you go and draw sketches to achieve those. And then you, as a skeleton, and then you build your parts on top of that skeleton. It's really fun. And where does the LiDAR scan come from? From my cell phone. I use an app. I use an app called, I've got an iPhone. I know I'm not fancy.
That is so cool.
And I use an app called Polycam, which is like a little LiDAR scanner on your phone. If you've seen my defect detection workflow, you'll see that I did a LiDAR scan of my shop, my garage, and I use that as a background for training an AI.
I don't think Zia believes you.
There are other LiDAR scan softwares, so I don't be confused. Polycam works well. The thing I like about it is that if you have a premium subscription, it exports directly to USD. Yeah. So it's, just bring it right into your scene.
That's great. Is that like very expensive or not too bad?
I should probably know that because I'm paying for it. And I must have paid for it by the year. It's $80 for the year.
Oh, okay. That's not bad.
It's like $7 a month. Yeah.
That's
Or you can
good,
do
actually.
$15 a month.
So it's about a creative cloud license for a whole year.
But for what is the Creative Cloud license? How much is that? Isn't that much a month?
I don't know.
I don't know how much a Creative Cloud license costs.
That's a good question. I
think
just
it's
have
more
an
than
automatic payment. So
yeah. Now, so there are other apps out there. There's like no best LiDAR or scanning app. Some are better at the photogrammetry. Some are better with the LiDAR. Some are better with small objects. Some are better with big objects. And so I guess buyer beware, or buyer be aware. Choose the best one for you. But there you go. This is a LiDAR scan I got from their software. And so just trying to do a layout here, and then I imported it into CAD or into Omniverse. I was trying to use I got a 3D mouse that we don't quite support yet in Omniverse. And I set up a simulation. So it just turns to the right and drives, but the suspension's working.
yeah, you watch that drop. Ooh.
Okay, I got too crazy with it there.
You gotta watch it drop.
And if I hold on to it, I can tease it a little bit here. Oh, come on. Oh, it's having none of it. Okay, anyway. Yeah, it just drops. And then the next step is there's this really cool demo. Let me see, window. We're way off top. We're way off track, but this is so fun. Demo scenes. And I don't have an Xbox controller with me, but there's this really cool, where is it? One of these demos. No, it's not that one. There's a demo in here that lets you drive a little car, like a little Lego car around. It's so cool. Simulation partitioning.
Would it be under
content.
complex showcases?
No.
Yeah.
No.
Lego Technic
Oh,
Buggy.
yeah, that's it. So if you've got like a video game USB controller, you can load this scene. And you can use your controller to drive this thing around. It's so cool. I don't think the arrow keys work, but let's find out. We'll try it. I'm hoping. No, you got to have the controller. A gamepad is needed. Yeah. And and so what I want to do is grab the code out of this physics demo, and in whatever car we rig up, whether it be the Lego car, or sorry, not the Lego, whether it's the RC car that you would be able to build yourself, or if we do the Sierra Cars race car, which you could buy yourself, but it would be a little bit more expensive than building an RC car. But either way, I want to make it so we can drive it around a terrain with a gamepad. I think that'd be so cool. And as we're driving it around, use these extensions, tweak them, so that we can harvest loads from that car as we're driving it around. And then use those, once again, to feed into the topology optimization that we're going to all... So we're circling back, getting back on topic. Let's see here. But yeah, let's open up our scene and take a look. We would want to exchange... Me, crank slider. Don't save it. Wow. Hello and greetings from Peru. Buenos dias. Hope you're doing well. Yeah. I had a Peruvian friend. He would always talk about the hundreds of varieties of camote, which is a potato. There's like hundreds of varieties of potato you can get in Peru. Yep, he always bragged about that. Let's see. So here's our crank slider. Let's open our extension and see how well it's working. This is always the risky part, right?
That's the right one, right?
Yeah. Okay, so we're getting some kind of a bug here where we added this phi item, and now theta and transmission force are not even writing, and this one is off the charts. Phi is an angle. It should be in between 0 and 2 pi for sure. So there you go. Let's stop it. Let's try it. Let's figure out what I did wrong. I broke it.
You didn't do something wrong. It's more so we told the computer to do a thing, and the computer was only able to handle so much, you know?
There you go. I didn't do something wrong. It's just a happy little learning opportunity.
Yeah.
There you go. I told Eric the other day that he totally reminds me of Bob Ross. It's that energy, that positive, relaxing, but very informational tone.
You should see me coach my daughter's soccer team. That's the other side.
Oh, really?
No, I'm just kidding.
That's funny. I'm very. I love watching coaches work with kids. I see so many different styles of coaching.
Yeah. Let's see. It's so true. I'm a yeller.
Oh.
But I yell positive things.
Yeah, sometimes you have to though, because they have to hear above the noise to be able to hear the coach on the sideline. So
yeah, I try to help them get into their spots. Well,
yeah,
Here we go. This is what we needed. There are no mistakes, just happy accidents.
There you go.
Now we're talking.
Papa Chuck.
Let's see here. Let's go ahead and look at let's go ahead and let's put a stop in this and see. It seems like it's not.
We didn't get any errors, right, in the console log?
I didn't look at the console. Maybe we'll start there, huh? Console. Yeah, we got a couple of errors.
Well, it looks like physics. Nope, none.
5 warnings. Yeah, that's fine. Some of the joints are just a little bit out of position at the start of the simulation, but you'll get that warning even if they're just like just barely out, and that'll just happen sometimes. So let's walk through our physics event here. Let's see, what are we doing here? Let's just start at the beginning and see if we can find something that jumps out at us. Because we should be getting, well, look at this. That's got numbers. It's just an off scale. You see that? Those both have numbers. And phi has got the numbers that I expect under transmission force. So I wonder if I just messed up my plot ranges. Let's actually, as I look at that. So let's look at that next. So where's my theta plot is in the, well, that's kind of weird. My theta plot, I wonder if I overwrote theta plot with this phi plot or something like that. No. Not in that horizontal stack. Because if you look at this plot, it goes between 0 and 0.4 or something. This one goes between 0 and 3, which I would expect for phi. I'm just flipping something around, I think. This transmission force plot. Oh, look at this. Okay, we've got theta, transmission force, and then phi. Is that what we've got here? Theta, transmission force, and then phi. Let's look at where we're adding data to them. We're appending phi here. Theta data. That's right. I wonder if I attach the right ones. So the phi plot has the phi data. The transmission force plot has the phi data. That's not right. Oh. What? I don't have transmission force data up there?
Nope.
Oh, I don't. Which ones am I doing here? Heck, I got it all.
I think it wasn't transmission force. Yeah, the names are all weird.
Yeah, we got transmission force data, phi data, acceleration data, and theta data. Let's see how that looks. Acceleration data with acceleration plot. Theta plot with theta data. Underscore transmission. Oh, come on. Transmission force data. Great. And phi plot with phi data. That's a good step forward.
Although your transmission force data seems weird.
Like it's not recognizing it. I didn't save the file. Okay, there we go.
Yeah.
Sometimes it doesn't update the lint stuff until you save the file. Slider force. Okay, here's my physics step. I'm appending the slider force data there, but that's not what I want. Let's find the transmission force. That's going to be...
Oh, you're setting transmission force to self-feed data?
Oh, dear.
Oh, that's funny. You have line 215 and 216 seen backwards.
215 and 216?
Yeah, so you got feed plot dot set data to
Oh.
slider force, and the other one's to feed data.
Oh dear. And then transmission dot. It's definitely another way to do code. Yeah, a little rough. Sorry.
That's why I love this stream you guys do. And Ashley's also, Maddie's of course. Ashley's is interesting because she does it by herself, right? So she's typically alone, and
No,
you really get.
technically, that was almost not true because I popped in the last 5 minutes in the last stream.
Did you save the day on anything she's working on?
I did save it.
That's awesome. But that's what's great about it, though, right? You get to really learn from her learning by yourself. The way most developers are here watching or learning and doing the development also. So I think it's very, very real.
Yeah. So when are you going to start yours, Edmar?
That's a great question. I will have to come up with something very, very compelling, and I have to figure out who will be my savior at the last second to help me out.
Well, I will always be free for you, Edmar.
Oh, that's awesome. That's wonderful to hear. All right, now I really got to think of something cool. I'm definitely. I would love to fool around with doing something in the digital twin. Working on a digital twin of something that's kind of fun, like a hobby digital twin.
Oh, that'd be cool.
I
think it'd be so cool if we had. I don't know if we could even do this, but if we had like an Arduino with a temperature sensor.
Yeah.
And if we could write a web service for that and then draw that sensor data into Omniverse and do something with it, I think that'd be super cool.
That would be awesome. I have a few fish tanks here. This is the smallest one over here. But I thought it'd be pretty neat to figure out what kind of monitoring equipment we can get and make a realistic digital twin of one of my tanks, showing like the water temperature and all the cool stuff that you have to monitor when you're growing plants and supporting fish. But I'll think of something. That's a good idea. Papa Chuck has just offered to help me out. It'll be great.
There you go.
Okay, so the slider force is that, and then we know theta. And so if we remember, the transmission force, so theta is this angle here. And so the cosine of theta is this length. And and this is maybe the tangent of theta.
Yes.
And so if we take this mass force, I'm blanking out right now, divided by the cosine of theta is going to be this transmission force. Is that right? I think so. So we'll just say equals slider force divided by the cosine of the theta. Okay. And now we can say self dot underscore transmission force data dot append transmission force. See how that looks. Just saved it.
Oh, that's interesting. How comes the acceleration doesn't look so different from the transmission force?
Yeah, it totally should, right? Let's get theta plotting correctly. It's weird because I had all this working. And I blew it all up. Well, all but that last one. Let's start with... so the force is the acceleration times the mass. So that force is going to follow along with... it's going to follow along the acceleration. It would be like a mirror, right? Because it's just... the mass is constant. So it's just going to be like a scaled version of the acceleration. And this theta plot, let's take a look at that again. I wonder if theta is working right. No, it's just not getting a scale in there. So let's see if we can figure out why. So my range goes from 0, it looks like, up to 0.4. Let's look at our scale and see what our scale is on that theta plot. Oh, look at that. So theta, so there's something wrong with theta. Because see how it should be in that range between, like, a lot bigger than that. And so I think that because theta's messed up and it's just in that tighter range, it's just kind of mirroring the plot. What did I do to my theta calc? I think I remember something I did. Let's take a look at this calculation, because what I was doing before, let's see, where are we calculating theta? Right here. I was just setting AC directly as like 0, 1, 0, and now I'm actually calculating it. So I remember I made that change. So let's take a look at our numbers there and see. Because AC is AC, it should be 0, 1, 0 every time. Or really from A to C should be 0, negative 1, 0. But so let's take a look and see what we're getting as we debug here. Ah.
Oh no, Discord.
Right. Let's just take 2 steps here. Okay. Now we're normalizing it. It's essentially 0, negative 1, 0. Let's see.
Do you want the absolute value of the...
Of those vectors?
Yeah.
I don't know. Maybe that's the problem, huh? Let's change that code back to gf.vec3d 0, 1, 0. Oh, now we broke it.
Uh-oh.
What did I do?
You got a bunch of errors that kept spitting out.
Oh. Vec3f. Reducing floats.
Well, it's probably because you can't take the dot product of it.
Oh, yeah?
Or is it because you're normalizing it? No.
Well, see, B is a vec3f. C is a vec3f. Let's maybe read the error, huh? Oh, I saved it, though.
Oh, I see. You're trying to do a dot product between vec3f and vec3d?
Yeah, but I changed that line of code. Vec3f. Let's just save it again. Might have this. Sometimes if this happens and it's just not.
I don't think
It might be because I changed it when it was mid debug and now it's all off.
Yeah.
Let's relaunch. Let's detach and reattach. Let's start there.
Nah.
No, so yeah, it's not running my actual code. So sometimes you can just launch Visual VS Code. Nope. Relaunch Omniverse. Don't save it. That's wild. You hear that? Extraordinary behind the scenes says that his kids did a school project that was repeated on the International Space Station.
I saw that. I wrote back. It's incredible. It's amazing.
Oh, that's a great question from Zia. How do we know if VS Code is still attached? Let me show you. There's a cool little extension for that. This actually opens with VS Code already. So there's VS Code link tab right here. VS Code debugger unattached. Now if we run this, we attach it. I'll get this dialog here. There's a hint that it's probably attached. VS Code debugger attached. But I think that, I don't know if when it gets off, I should probably check that to see if it's still attached. But let's go ahead and see. Oh, we got to open our scene here. Great. And let's enable the extension. And then let's run it. Okay. There we go. Now we're talking. That's right. So it's fixed again. Well, those three are all working correctly. This does not seem right. Let's look at it. It should be something more like theta, right? More cyclical than spiky like this. Oh, unless it's going negative. No, it's not. What are my values here? It's not going negative and getting chopped off. But just to be sure, let's go to our plot. Our phi plot. We'll just go ahead and make it go from pretty much negative pi to pi and see what that looks like. If it looks, oh, no, it was getting chopped off. How about that? It's still getting chopped off. Let's stop this. That's weird.
Should it go that low?
Yeah, I don't know. The range on my plot is going negative. Let's just make it, let's do that again because it's looking better. I don't think it should. Oh dear. Wrong button. Let's go again now. This is weird. Like changing this. Am I on phi plot? Yeah. Keep making this range bigger.
Wait, are you making the range from greatest to least, or should it be going from least to greatest?
Yeah, so let's pause. My bottom value is what? 3, and it goes up to. These are negative values. It's just, I think there's maybe a problem with this plot. It's not even, these are negative values, but they're not showing up as negative. Which I'm okay with.
Zia's got 2 questions.
So z down to negative pi. That kind of makes sense. 2 questions.
2 questions. First one. Phi oscillates between positive and negative?
No, it oscillates between 0 and negative.
And then the second one is, shouldn't it be a sawtooth?
I don't think so. And let's just do we can do a little logic check to be sure, because I am definitely not always right about this sort of thing. Going from 0 to negative 4. Let's see how that looks now. What? I'm so confused by these limits. I'm just bamboozled here.
I'm more bamboozled than you are because you're making magic happen.
Yeah, but it's like not very good magic right now. Okay. See, that looks good. What the heck is going on here? Let's just look at another one. From 2.6 to 3.2. This is the lower limit. This is the upper limit. I've got my limits backwards. I think I'm flipping the plot upside down. Let's just go from -4 to 4. I wonder if you put the limits in backwards, if it like inverts the plot. Okay, that's totally what was happening. So no wonder, yeah.
Me too.
I'm confused. That makes 12 of us. So let's oh, what happened there? I don't know.
Wait, the accelerations. Wait, huh?
Got all bung. I don't know what happened there. All right. So let's now we can dial that in. So let's go here. We're going to go from 0 to 3.2. 3.2. It should be in that range. Let's see if he's getting caught off. Yeah, there we go. That's more like it. In transmission force, well, I feel pretty good about these plots. They could be dialed in a bit more, but we don't need to go down that path. Okay. Sawtooth. I guess, is that the sawtooth you expected?
Probably. But this is going from 0 to pi, right?
Yeah.
Okay.
0 to 180 degrees and then back down. And it really, that's one thing is I'm noticing this dot product we're using is only giving us like the positive angles. Yeah. So I think I'm trying to decide if we want to figure that out or just not worry about it. Because I think that really the whole point of this is to show that we can put sensors into Omniverse, that we can do these kinds of calculations. But it would be nice if, like theta as well,
I guess what would be interesting for me is, and maybe other people, is how is this important, or what benefit do I get from seeing these values?
Yeah. I think instead of spending too much time debugging that angle, let's go ahead and move forward with the use case. Is that what and let me know your thoughts here. If y'all want me to go through and debug this, we can debug this, but I'm thinking let's move forward and let's show where it's used. And let's see here. So this is where it's used. So at this point, what I now have is I know phi, the angle between this link and this crank arm. Can I do like a whiteboard? I don't think I can do a whiteboard. And let's see, I don't know how to draw on my screen. Can you draw on your screen in Windows?
I don't think so.
Yeah. Let's just do paint, I guess. So let's take a look at this. So here's that crank arm. And here's that link. And we know this angle phi. We also know this force right here. Call it F. Actually, P is more typical. So now if we redraw that, we can say that we've got this crank arm turned this way. It's got a load P into it here. And where this pin is, we can say that there is a restraint on it. Say, hey, that pin is fixed. And we've got a force P coming into it right here. And so now what we can do is we can bring a CAD model of that arm into CogniCAD, and we can apply a number of forces we've harvested from our scene onto that model, and we can do a topology optimization just like this and reduce the weight of that crank arm. What do you all think?
Now, is that so? In reducing the weight, what is that in turn? Like, what's the benefit in reducing the weight?
Well, this is a simple crank slider.
Right.
So I don't know that we actually care that much about this one. But in a car, reduced weight is this lower fuel economy. Or that's improved fuel economy for one. Or if you're reducing weight, that's also improved performance for higher performance cars. And if you can reduce the weight, especially of suspension components, if you can do that in a smart way, that's going to reduce the forces throughout the whole system. And if you can reduce the force, because you're going to have lower momentums, right? Force is equal to mass times acceleration. So if you're accelerating smaller masses, all of your loads reduce, and then you can get improved durability. So if I have a design that's inefficient, it's got extra mass, that's not really adding strength, that's just increasing the loads throughout my system and then I've got to beef everything up to respond to that heavy mass. So if I just arbitrarily make things light, yeah, of course, if you end up with tinfoil parts, they're not going to be more durable. But if I come up with, but if I can have more efficient designs, it's gonna also be more durable. There you go. So let's see here. So now, what's that?
Today I learned.
Yeah. So now what we can do? Should we go ahead and just try to build up a load case in here a little bit? Let's see. Should we see how this works?
Yeah, I'd be curious.
So let's go return to cabinet. Let's create a project. And we want an isotropic. That just means that it's, actually, a second. An isotropic this is just your regular structural analysis. So variety of loading conditions. Let's just do that one. Does that work? Oh, there we go. Okay, so now we need a step file or an STP file. So let's see here. Let me just open up my file system a little bit and see if I've got those copies. I do. Oh, but they are all. Well, I have a step file here. Okay, so I don't really have good step files. So let's go ahead and use NX to get that a step. So I can open. Oops. Just opening this assembly here. see. Let's open. We got all files. There we go.
It's a good question. What is a step file?
A step file is a neutral CAD format. So you've got, and it typically represents just the boundary shape of the parts. It doesn't. So if I actually design something in CAD, I'm gonna be drawing lines and points and surfaces, and then I turn those into solids. And with a step, it's just the outer shape. So I've got this open here. Let's grab that crank. Let's open a new window by itself. Here we go. This is the crank arm we want to optimize. Say File, Export. Well, we could do Step or STL with this. I'll do Step though. And going off screen, just usually don't show my file system if I can avoid it. Just try to be safe.
It's a secret.
Tippy top secret stuff going on all the time over here.
Yeah.
That's fine. And then I'm going to export this to just right here. Make a new folder.
Speaking of top secret, we got a cool top secret project in the works that will be in preparations for the keynote at Computex in a few weeks.
Ew.
Everyone should set their calendars for that. Let me see. Maybe I can share my screen really quick while Eric's getting that ready. Yeah, May 28th. It's on a Sunday. So no excuse to miss it. Let me see. We have a nice slide that was prepared by Greer. Thank you, Greer.
Oh, it didn't work. It failed. So we'll just do an STL.
Any clues for marketing?
That's a good question. I actually did ask that. And even marketing doesn't know really everything's going to be discussed at the keynote yet. It's still very much in progress. Yeah, obviously we're always working on amazing things here. So they're just trying to finalize what we can share on May 28th. But it should be good because Jensen's keynotes, when he's giving them himself, are always pretty spectacular. So we just added this to the Ed event calendar. So if you're subscribed to the Ed event calendar, you'll see it there. Exit here, and then we have a nice web page for it. And then, like I said, we added to our Ed event calendar, so it's there.
There we go.
Do you have a link for the ad event calendar?
Yeah, let me post it in the chat.
Oh, that's the wrong one. Create project, isotropic. Choose file. CAD.
That's a good question from Zia. I just posted the calendar in both chats. Yeah, we have a really cool live stream this afternoon, actually kicking off in not too long with the AECO team, part of their AEOCO series. We're going to have Bentley and also Cesium. Speaking about photogrammetry we talked about earlier. So both those great partners using Omniverse will be on our live stream today. On the ad event calendar, it is posted, so you can add to your calendar very easily. And then I just got this secret scoop, another top secret thing. We're going to be announcing our next community challenge next week.
Oh, cool.
Yeah. So
why didn't you tell me?
I just found out during the stream. During the stream, I actually tried to double duty, so I'm doing work while listening to you guys. But so it was happening in a concurrent chat. but this will really appeal to creators out there and artists. So we have a channel called Community Challenges on our Discord server. So we're going to post it there and post on the forum, of course. But get ready. It's going to be a really fun one.
All right. I almost forgot. We only need to do a little bit of design work here because you need to design like these fittings and things where you want some work to be saved, sort of, right?
I see.
So what we should do here is open up NX. We'll do a little bit of work here.
Can you do it in 10 minutes?
No, probably not. But we'll just get a little bit of a start. So just let me just in 10 minutes. Let's explain what we'll do next time. How about that? So we don't end up with too bad of a cliffhanger. All right. So this is a design domain that I did for that other part, and basically, if you don't, you got to design these green. It says non-design. What that's saying is that it must have that material at the end. And if you don't put any spaces like that, it will just whittle everything down. It'll whittle those joints down to nothing. And so if you look at this, we have a bolt through here. You've got to have some material all the way around that bolt. Otherwise, the design is not going to actually work.
Hmm.
And so what we'll do is we'll just draw a little cylinder around this, and we'll do a little cylinder around this. And those represent some space that absolutely must be there at the end of the design. And you have to have those. You'll want to apply our boundary conditions, our loads, and our restraints to those non-design domains. So let's go back to this. So you can see we've got those, right? This is our design domain. And for us, our design domain, excuse me, we could actually start with this shape, but in my experience, if we can let this bow out a little bit, it's going to come up with a more efficient design. So we'll probably make it even a little chunkier and let it kind of just like go out a bit more. That'll be kind of fun. And then what else we got? We've got these other mounting positions on this. But on our little crank arm, we'll just have those two spots, just those two mounting bosses, if you will. And then we'll pick a material. This I used ABS. We'll probably do like I like aluminum. It's just a cool material. And in this case, there are these automatic load cases. Let's see. If I go to load cases, though, I can define known load cases. And I can add a load case, and I'll just go in by hand and add the load cases to this thing. So I can be like, save it, I go back, boundary conditions. There we go. So these are going to be the stuff that's kind of stuck, if you will. And then for loads, we'll click on this part, for example, and we'll apply a force, and we'll have to come up with some magnitudes. We'll use our angles to kind of figure that out. So we'll apply loads to other things. And from there, so those are our load cases. And you can do more than one load case, but we'll just do one just for fun. But realizing that in the real one, we would kind of connect the two and feed any number of load cases into the system. And then, save that. And then, then you've got some, what do you want to get out of this? And we can choose some objectives and it'll design for us. It's really cool.
Could you 3D print it afterwards?
Totally. I even have a 3D printer. I'll do it. Yeah. I got this really cool resin 3D printer. It's got like a 8K resolution, which is in the micron range.
Oh.
So they're not the strongest materials, but the parts look like injection molded parts. It's so cool.
Wow.
And it wasn't that you can get them on Amazon. It was for what it prints out. I feel like it should be tens of thousands of dollars, but they're not. They're more like in
That's
the hundreds
awesome.
of dollars. Yeah.
Wow.
So
Huh.
fun. And it's warming up. So it's actually been too cold to 3D print stuff out of resin because it's been the winter in Utah. So it's time to warm up the 3D printer, see what we can do. And so this is actually, now that we've got some of the regulars here, I just wanted to ask once again before we close. So after this, we're almost done with this project. The thought is I want to go ahead and maybe rig up a car with physics and get it so we can drive a car around in Omniverse. And my question for you is, would you rather we did that with a remote control car, one that you could all buy and make yourself after we're done? Or would you rather we work with the Sierra Cars race car it's a lot cooler, bigger car, and you could buy it yourself, but they're expensive. And anyway, so would you rather do it with the Sierra Cars or with a remote control car? What are your thoughts? So Zia likes now you can actually buy the Sierra Cars as a kit too. You can buy like the frame from them and parts from them and build it yourself. But I think you're saying remote control car. Is that right? I think that's what Zia is saying. Who else has got a thought on that?
I want a remote control car.
Jen wants a remote control car.
Heck yeah.
Yeah, I thought it'd be cool with a remote control car. And this should be a question for you all out there. Well, maybe I should know this. It seems like we could get a Jetson. Oh, this is a fun idea. Let's build this remote control car with a Jetson on it. And I wonder if we can teach it to drive itself.
Probably could.
Would that be a cool project?
You could do that.
Yeah. Let's work on that project. Let's make a self-driving remote control car that anyone, yeah, it's going to be a couple $100. Don't get me wrong. It's not going to be free, but I think reasonably someone could build this car. And I wonder if we could have like a little mini contest of our own to see who can train a car to drive around a given track. There's actually,
I love it.
You know what? There's actually an NVIDIA contest that I don't know if it's still running, but there was already a specified track. And so we should make an Omniverse scene with that track. And we should let people have a little contest to see who can train their car to drive around that track the best and the fastest. Anyway, I think it's a fun idea.
Big goal.
But let's start with wrapping up this project, right? We're close. I think next week we'll be able to design those bosses, import everything into Paramatters and run the optimization. It won't finish during the live stream, but I think we can wrap it all up and then the following week we'll just show the results and move on to our next project. So cool. And ending early without a cliffhanger. How's that?
It's good. It's good. Now we end on time and we get a break to run around the house before next meetings, right?
Yeah, that's right. Go get a quick drink of water or something, huh?
No, coffee. Edmar, you're muted. Nobody can hear your wonderful voice.
Sorry. These are our upcoming streams. A lot to look forward to. We've got I mentioned earlier, the Bentleys and cesium one. That's today in just another hour or so. And then we have Maddie doing his developer office hour for all you Python devs out there. That's tomorrow. And then, of course, Ashley, we mentioned earlier, she's going to continue on with her Learn With Me series, Art in Omniverse with Python Part 2. Part 1 is obviously on our YouTube channel already. And then the Isaac's team is well into a month of their weekly live streams every Tuesday. So next Tuesday, they'll be continuing their Isaac Sim Robotics live stream. It's a rotating cast of Isaac Sim developers, so a lot of fun to watch. each covering a different topic. Yes, and then next Wednesday we've got Adobe coming on our Wednesday live stream, which is going to be awesome. We're finalizing details with them on that topic this afternoon, so I'll update this at event calendar shortly. But yeah, so if you're not already subscribed to this calendar, definitely do if you want to see all the latest. And if you have any ideas on upcoming live streams, what we should cover, just shoot me an email, edmar@nvidia.com. Let me know what you want to see. We'll put it together.
Cool.
Sweet.
All right.
Until next time.
Until next time. Same bat time, same bat channel. We'll see you all next week.
Well, I'll see everybody in an hour in the next live stream. All right. See you guys later.
All right. Have a good one.